Welcome everyone to the IF seminar today. Welcome to the audience and also to the online audience. The topic for today is simple technologies for wastewater treatment in extreme conditions, and we're lucky enough to have Professor Jaime Martí Herrero. And for summary of the talk it's going to be about simplified technologies, accessibility, prioritize software efficiency. So enabling access to a sector of that population that otherwise would have had not the opportunity to use these technologies is very important. So the treatment and reuse of organic waste, including its conversion to energy and agricultural resource, can be carried out through low-cost biodigesters. And this is going to be one of the main points that will be treated in the seminar. For the physical audience, we will have a Q&A section at the end. For the online, you can post it on the chat box and we will read it at the end. And after this, over to you, Jaime.
Okay, let me see. Are you listening to me?
Yeah.
Yes. Okay. Good morning to everybody. Here is about 9 o'clock in the morning. I am talking from Ecuador. First of all, I want to show you where I am. Let me see. Yes, okay. Here is where I am. This is the jungle in the Amazonia in Ecuador. To put just in the map where I am, Ecuador is this small country between Colombia and Peru. Ecuador is divided in 3 main regions. One is the coast region in the west, is tropical area. Later you have in the middle all these mountains that we have volcanoes that achieve more than 6,000 meters above sea level, and later the Amazonia of Ecuador, that is all on the west, the tropical forest. We are now here just in the transition between the mountains, the Andes, and the Amazonia. Here is a zoom. You can see some volcanoes here. This one is the Cotopaxi. It's nearly 6,000 meters above sea level, and 80 kilometers to the east. We are here in Tena, in the university. This is a public university, very young university. It is in the middle of the jungle, as you can see. We are just 8 kilometers from the main city that is close to here. Is the city is Tena. The university is very focused on sustainability and biodiversity. We have only around 1,800 students. 1,800 students and 100 teachers and professors. So we are very small, but very focused on these topics, no? Mainly, as I said, biodiversity and sustainability. One of the themes of this university is that we are surrounded by indigenous people. All the communities around the university is we found indigenous people. They are Quechua, Naporuna people. So a lot of the research we are doing in the university is to resolve problems that these communities have, and also to learn from their knowledge, ancestral knowledge, for example, about plants or some animals, things like that. So the first thing I want to talk to you is about these simple technologies for wastewater treatment, and mainly I work with digesters, and this means that I am working with anaerobic digestion. What is anaerobic digestion? It is a natural process. It's a complex natural process. It is happening in the nature, in the lakes, for example, but also inside our stomach. What we need is a consortium, microorganisms that are able to treat the organic matter and transform it to methane. And this is happening without the presence of oxygen. That is the conditions to produce methane. methane from organic matter. This is happening inside of us, inside of any of the animals that we have around. So we can say that we are digesters with legs. It's very similar. Also, we are producing methane, and all of us know what I'm talking about when we produce methane. And the idea is just to replicate this in a controlled conditions, in a controlled system that is called digester. So usually in Europe, you will find this kind of digesters. They are very big digesters. What they do is just to treat waste, organic waste from farms. And usually they are focused to produce electricity. What is happening is that in Europe, the idea is that you have to heat these digesters to achieve 35 degrees. The idea is as the microorganisms came from the stomach from animals, these microorganisms have been evolving to have a very good performance at around 35 degrees, the same temperature as the body of these animals. So usually in Europe, all the people is trying to heat the digesters to try to give good conditions for these microorganisms. Also, sometimes you can go further and heat the digester to more than 60 degrees. So this is what we find mainly in Europe, mainly in Germany. Germany is a country that has more amount of digesters. We are talking about now should be something like 20,000 digesters of this kind. They are very, you have to invest a lot of money to build one of them. They are very big infrastructure. And they are focused on, before they were focused on the production of electricity, but now they are focused on the production of biomethane. That is the same gas that you can have in your kitchen for cooking. So this is what is happening in Europe, but it's not the same that is happening in the rest of the world. In the rest of the world, we have low-cost digesters. Here I am showing just two kinds of digesters. The tubular digesters are made of plastic, this both, and the most famous digester is this one, is made with bricks, and it's called the Chinese model. You will find more than 40 million of these digesters in China, for example, or something like 8 million of these kind of digesters in India. Also in Africa, all the countries, Kenya, Tanzania, there is a lot of countries that have thousands and thousands of these kind of digesters. And in Latin America, mainly, we have these other kind of digesters, tubular digesters. These digesters, they are not heated, so they are not working at 35 degrees. They are working at lower temperature. So usually when you go to Europe and you say that you are working with digesters that are not heated, what the people say is you are working with a very low efficiency in these conditions. That is what they say, and also they have demonstrated in laboratory conditions. We can find in literature that the amount of methane that you can produce against the temperature show this kind of results. So what they are saying in laboratory results is that when you work around 15 degrees, below 20, you are producing very, very few amount of methane. So usually the people in Europe say it's not feasible to make methane in low temperatures. But what happens when we go to the field and we measure real digesters working in low temperatures? Here I show you the results from a digester that was 8 years old, was working, and was fed with pig manure, and was producing 400 liters per kilogram of volatile solids. That is a lot. Why? Because if you remember the last graphic about the other paper, they were saying that in laboratory, in that conditions should be around 50 liters, and we are producing 400 liters. And the reference for pig manure is at 36 degrees, so the best condition is 323 liters. So what is going on? We are producing a lot of biogas, a lot of methane in very poor conditions, temperature very low, 17, but we are producing as much methane or more than in the best conditions. So we have a problem between laboratory and real life, what I used to say. So just 1 year ago, this paper was published where they talk that the important thing is not to talk about mesophils, microorganisms, or psychrophils, microorganisms. We have to talk about that in this range, around 20 degrees, all these, not all, but a lot of them, all these microorganisms can still work at low temperatures. And also all these microorganisms that came from cold climate regions can work also in these middle temperatures. What we have is that the microorganisms can adapt to the new conditions and can be working at low temperatures with very good performance. The difference, the real difference, is that they make all this methane, they make it slowlier. So they need more time to produce the same amount of methane, respect if they do the same in warmer conditions. So, for example, here we publish a paper where we took a inoculum, a microorganism consortium, that they were working before 35 degrees. We gave to them like paper to eat. So what we found is that these microorganisms, they were working very well at 35 degrees, that is the degrees that they were living before. And when we go down with the temperature, they were producing less and less amount of methane. But what happens if we take a microorganism that has been working before at low temperature and we began to heat it to give them more temperature? So we began with a psychrophilic inoculum, and what we have is that they have the best performance at 15 degrees. And when we increase the temperature, they have a worst performance. So the history of the inoculum is very important. From where are you taking the inoculum that is going to make this process to transform the organic matter in methane and biogas? And usually this kind of history of the inoculum is not taken in account in laboratory, because usually in laboratory, they want to be very fast, to get very fast results to publish very fast. And if you want to publish papers very fast, you need to work with high temperatures. So usually, we don't know what's going on with low temperature conditions. We have a lack of information. Here we have a paper, for example, that they are talking about that we can work even at 4 degrees to produce methane, 4 degrees Celsius. So at the end, what we need to know is that the consortium can be adapted to the new operation conditions. So you can take inoculum from a digester that is working in hot temperature. You can take it to cold climate, but it's gonna take time to evolve and to adapt to the new conditions. So we have to trust these consortiums and to give them time to adapt to the new conditions. Now, with these ideas, I want to present myself. I am Jaime Martí. This is my first digester I built in Tenerife, in Canary Islands. Just if you see the date is more than 20 years ago. That was my first digester. Later, I began to work with in Bolivia with Quechua people, and I began to install a lot of digesters. At the beginning was more just to try and error and try to improve the technology again and more errors. Try to make very simple technology to be able to install these systems with very poor people and indigenous people in Bolivia. Later, I tried to transfer these digesters to the cold climate regions. You know that in Bolivia, they have more or less 5 million people living over 3,000 meters above sea level in a very poor, very difficult conditions. So we try to improve the technology to go there and to make it feasible, working system. And at the end, I don't know why, I finished installing the highest digester in the world, the highest wastewater treatment plant in the world that is here in this mountain, and I will talk later about it in Huayna Potosí. So what was the idea to make digesters in Bolivia and now in Ecuador? The idea was to produce biogas for cooking. This with a small digester, just fed with manure from 2 or 3 cows or from 6, 10 pigs, can be enough to produce enough biogas for cooking. Also, the people who have pigs, they can use the biogas for heating, to heating the baby pigs. And sometimes the people are using the biogas to run small motors, engines, just to, for example, to cutting grass or pumps, water pumps, or a small machinery that you have in these small farms. So you can use this kind of biogas on all this stuff. One of the challenging things was to work in these highlands in Bolivia. This is the highland, the Altiplano is called. It is very flat, but you are at 4,000 meters above sea level. So here is the most of the people are Aymara people. They are indigenous people in very poor conditions, but there is a lot of people there that own sheep or cows. So we can take the manure from this animal and to produce biogas, for example. We began to work with the public university in La Paz, in the capital, and we built several digesters, real condition digesters, just to try different mixes and different ideas. We were working there for 6 years. I was living there in La Paz. And what we found is that we can produce biogas putting just the digester inside this greenhouse with the walls made with adobe walls, we call it. It's a mix of sand. This is what you find inside this greenhouse. There's a tubular digester where they just have to put the manure mixed it with water inside the digester, and you will produce enough biogas for cooking for one family every day. No, they will have enough biogas. But what we found with the time is that this greenhouse was damaged by the climate, because it's very difficult climate at 4,000 meters above sea level. So we decided to change the greenhouse. For example, the plastic with this polycarbonate layer is more harder and is more have more time working. So we also improve the insulation of the trench for the digester. So you can see here, and in these conditions, you can have a very high temperature inside the digester, even with temperatures -0 degrees outside. So we have made a lot of heat transfer models. We have published a lot of paper about the thermal performance of these digesters, just using solar heating, so no active heating devices. And what we found at the end is that we can put the digester in the same temperature than the maximum ambient temperature that you have in a place. So I don't know in London what is the case, or in Leeds or in Oxford, but if the maximum temperature during the winter is, I don't know, 15 degrees or 12 degrees, you can achieve this amount of temperature inside the digester if you consider the insulation, if you consider the greenhouse, and the black color for the reactor. So that was a good, for us, is enough to have around 15 degrees inside the digester to run a digester. Other thing we tried to improve this, the amount of biogas we were producing, is to put inside the digester soda bottles, plastic bottles. Why? The idea is that these microorganisms that are inside the digester, they are not just swimming in the slurry. They are attached to the surface inside the digester. So what happens if we introduce some material to increase the amount of surface inside the digester? So we will have more amount of biofilm or more amount of microorganisms. We did that, and what we found is that we can produce 43% more biogas when we put bottles inside the digester. And when we say bottles, we are talking about bottles, plastic bottles that you can find in any place as rubbish. So everything was going okay with this research, with bottles, with the thermal performance. And one of the ideas we were not sure is what this bottle were doing. They were doing like a filter, doing more, increasing the retention time of the solids, or they were really giving more space for the microorganisms, a more surface to be colonized. So we make some more research in other digesters here in a slaughterhouse with the wastewater from a slaughterhouse. And finally, we know that it's more important that the biofilm creation, the colonization of these bottles by the microorganisms is the main effect. But also we learned that to put these digesters in series, so divide the digester in different states, is better for the performance. And also we learned that for the final treatment of these wastewaters, we need wetlands. We need to add something more. The digesters are not enough to treat properly this, usually the wastewater. They produce biogas, but it's not enough this technology to give the necessary treatment of the wastewater. So with these ideas, for example, we went to these extreme conditions. This is a desert in the south of Bolivia. Is 4,000 meters above sea level. Sometimes you can see like this picture, but sometimes you can see like this one. So during the winter, you can achieve around -20 degrees during the night. So the electricity company proposed us to build a wastewater system here in this condition, because they have a place where they are trying to produce electricity from geothermal source. So they need a wastewater treatment plant. And we did what we know to do, that is this big greenhouse with adobe walls. And inside this greenhouse, we put some digesters. We put 20 centimeters with insulation. So this is a lot of insulation. We also put inside each digester 300 cutted bottles to increase the surface, and a small wetland at the end of the system. So that was the first time that we were introducing wetlands inside these systems for the wastewater treatment plants. One more system that was very complex system was this one in this mountain. The Huayna Potosí is more than 6,000 meters above sea level, and there is a refugee at about 5,000 meters where they have no wastewater treatment plant. Every day, more or less 25 people is sleeping here to go next day to climb to the top of the mountain. So they were looking for an alternative for the wastewater treatment. So we decided to make a digester and a new bathroom. So here is what you see. Here later we built the toilets. Here are the digesters, and here is the wetlands. So what was the idea of these digesters? The idea was to make something like a cooking box, solar box. So it's very similar, the idea. So, but we are not gonna cook food, we are gonna cook other thing. And later a final wetland, just to try to improve the treatment of the wastewater. This is the tanks that we use. It's very difficult conditions to install this at this 500 meters above sea level. We were separating the gray water and the black water. Black water is the one that comes from the toilet, just from the toilet, and gray water is that one that came from the sink, or when you clean your hands, or from the kitchen. That is gray water. So here we were just putting black water inside the first 3 digesters, and in the 4th one, the gray water was coming in. So this is a normal performance in 2014, a normal day performance. And I have been here just 1 month ago. I went to Bolivia back to see what's going on with this system 10 years after. This is how it is. It is still working, the system. The people is happy, but we are now taking some measurements to know how it's working, how is the efficiency. The first thing I did was to put some sensors just to measure the temperature inside the greenhouse, to try to measure the temperature of the tanks. And here I can show you some data. Just have taken 1 month ago. During the night, we are -3, -2 degrees, but the tank is around between 10 and 5 degrees. So it's not bad. We are 10 degrees over the ambient temperature. That is a good point. And we can improve this greenhouse because I found that we have infiltration from outside. You can see here there are some holes in the wall, so we can improve the system. We also took some samples of water, so I hope in next weeks I will have the results to know what's going on with this system. Also want to show you these pictures because I have been going to this mountain for several years. So this is the glacier, but this is the glacier in 2010. When I went to install the system, this is the glacier in 2014. And now, when I have gone just 1 month ago, this is the glacier. So it's just here, 2024. So we can see the climate change running just in 14 years. It was crazy for me when I compared the pictures from the different years. But let's go back to the jungle. Let me show you. We have also experience in the jungle that also are extreme conditions. These are 3 digesters that are treating the wastewater from part of the university where I am working, the IKEAM University. And it's just a pilot project where we were trying this kind of systems in these conditions, tropical condition. We also had wetlands, and we decided to, well, here you can see how is the water, how the water come into the system, how go outside of the digesters, and how go outside of the wetland. So it's very easy to see that it's working. We transferred this technology to Quechua people, a community that they had before. They hadn't a water system or toilets or bathrooms. There were nothing. They were just going to a small caves to take the water. There were just 1 toilet in all the community. This 1 toilet is just a place with a hole and goes to a bigger hole that is behind this small house. So they were taking water from the rain. So we decided to make a integral project. Before they were taking the water from the rain or from these small caves that you can see here. So we joined to them to work together and decide to make a drinkable water system and also toilets and also wastewater treatment plant for each family, because they not live together. They live 50 meters, 100 meters one to each other. So we began to work with them. The first thing we did was to take the water from the caves, put some filters, sand filters, and chloration. With them, we worked with 2 kilometers of pipes to take all the water, drinkable water, to its house. And later we began to build small toilets with shower and also with a sink to clean the hands. This was the model of the toilets. We began to build them, 35, because they are 35 families. This is the process as we were building them. Different. It's people just make different, I don't know, design in the doors and different materials, but all of them are similar. And what happened here, that the gray water, that is the one from the sink and the shower, go directly to a wetland, and the black water, that is the one that is from the toilet, go to a digester. So yeah, more systems. The digester, we built the digesters with them. We teach them, and we were working together. We built a lot of digesters because there are 35 families, and we put 2 digesters per family. That was a lesson learned because it's too much work. So here we were installing these digesters. We were building a lot of digesters, and at the end, this is what you have. You can see here 2 small digesters and 1 small wetland, okay? And this is working. Here also, you can find the toilet in this back. Later, 2 digesters and a small wetland. And this has been this project 2 years ago. This is still working. People are happy. They have fresh water in the house, and also they have toilets, and they are treating the wastewater. So, for example, this we decided to make not 2 digesters because it's a lot of work. So we decided to make only one digester. And the first system was in my own house. This is the digester that is treating the black water in my own house now here. And from the digester, later goes to a small wetland that you can see here. I am measuring the amount of biogas that my family is producing. We are producing more or less 67 liters of biogas per day. It's not too much. It's 2 adults and to my daughter and my son. And we are now measuring what's going on with these systems. Which one is the best system? It's better to put 2 digesters or just 1 digester. So we have been measuring different systems that we have found in the rural area here in the Amazonia. One of the systems that we found is that people that have only 1 tank, or some people has 2 tanks to treat the water. This is very similar to a septic tank. So we have been measuring them, and what we found is when they have only 1 tank, the chemical oxygen demand is very, very high. The regulations says that we need only 250 milligrams per liter to be considered treated. But here we are talking that we have very high numbers. Also, when you have 2 tanks, you have very high numbers. And when we have different designs of digesters, and at the end, wetlands, is when we achieve a number below, lower than these 250 milligrams per liter of chemical oxygen demand. So when we compare what happens when we have 2 digesters and a wetland, or just 1 digester as my house and a wetland, and at the end we have the same. You can see the numbers. So we can go, the next step is just to be installing just 1 digester, 1 wetland, because it's not necessary to build 2 digesters. So this is just the end of the presentation, just some ideas I want to share with you. We have problems with the laboratory conditions. People are thinking that what happened in the laboratory conditions can be extrapolated to the real life, and it's not. We have to be sure that laboratory conditions are laboratory conditions. And in the real operation of the system, we found different performance because it's more complex. The reality is very, very complex. Happens a lot of things in the same time. Not everything is controlled. And this is one of the main problems we have had, that the literature do not recognize that there is an opportunity in working in low temperature for this kind of wastewater treatment plants. So we need more research outside of laboratory, but this is the problem again. Usually the people want to publish papers, and this is faster if you do it in laboratory. When you go outside, when you go to work with the people, it's more difficult, it takes more time, but the information is more important for me from the real conditions. One of the challenges is how to keep these technologies very simple, but also efficient. This is very tentative to complicate the technology. It's very easy to say, we just need to put one motor inside, or one pump, or one new filter. No, please try to keep it simple. If you complicate this technology, you make it more complex, for sure, it's not going to work when you go to a rural area. It's going to work perhaps in the 2, 3, 6 first months, but when you go back after 1 year, 2 years, or 3 years, for sure, if you had put a complex system, it will not be working. We think that usually you will find that there is sanitation projects for wastewater treatment. And also there is different projects that are giving drinking water to the communities. And we think that we can join both type of projects because they are together. How to put drinking water inside the family, and also how to treat the wastewater that the family is producing once you gave them this drinking water. So we think that we can go together with these kind of projects, integral projects. From the research point of view, psychrophilia is the great misunderstood and undervalued situation, mainly in Europe. That is why I try to say to you, not here in Latin America or in Asia or in Africa, where most of the digesters are working in low temperatures. But in Europe, I think there is an opportunity to improve the knowledge and the technology in these conditions, in these cold conditions for anaerobic digestion. So thank you to everyone. That's all I wanted to share with you. So I am very open for questions or suggestions or ideas.
Okay. Thank you so much for a great talk. And now we go into the Q&A for the online audience. I repeat, you can pose a question into the Q&A and we will answer it. But now first in the live audience, I don't know if anyone has a question. Oh, yeah, perfect. Do you trust your voice or do you want the mic?
No, Jaime, can you hear me? Yeah.
Yes.
So I thanks for a great talk, and I see a lot of practical solutions here, and I think that's what you're all about. So it's really great and really interesting. I've got lots of questions. I'll just start with one, but I might come back. In terms of water quality, I know you compared your anaerobic digester system with some conventional septic tanks. But did they have the same inputs? I didn't see any data on the input quality of the water going into the septic tanks versus the digesters. So that's the real test. You know, if you've got low COD coming out of your digesters, you need the input data, the input concentration need to be similar in order to make a comparison, right?
Yes, in that case, we were measuring different families. So we have been working with 12 different families, just measuring along the time. We measure the influent and effluent for 3 months. The idea is that should be very similar. There are families like my family, like the families that are surrounding me. So we hope that it's more or less the same. I know the numbers, what we found are not very different, no? When 3 different people give this amount of COD, these are 3 different families also. So I think we have a tendency, no?
Did you measure the influent concentrations of COD as well as the effluent? So you're just showing the effluent right now.
The influence should be something like these big numbers, because we don't measure the influence. It's very difficult to measure the influence to the system because it comes from the toilet.
Yeah.
So it's very strange. You know, it's not easy to measure it. But look, these high numbers that we are having in the first tank, for example, or in cases in the second. So this is only black water. So this is why they are very high numbers, because only is effluent from the toilet. It's not the sink or the shower. So this is the influent, more or less. Should be.
It makes sense because the digester is converting organic matter into methane, right? So
Yes.
you should see a COD drop during the digestion process.
Yes. Yes. That is it.
One other observation. I don't know whether you've got any data on ammonia. I know with AD, the digestate often has very high ammonia concentrations. So I don't know whether you've been measuring, you've got any measurements of mineral nitrogen in the systems?
We have been measuring that also. I didn't show here, but we are preparing a paper about this. But we have no problems with nitrogen. The problem is pathogens. I don't know how to say in English.
Pathogens.
Pathogens.
Yeah.
We didn't achieve the regulations with neither of the systems I show here. We are over the regulation number. So we have to see how to improve this final part only for pathogens.
But I guess if in the systems you're showing there, if your effluent is just going into a soil soak away, then it doesn't really matter, right? The pathogens will
Yes.
go into it's only when you're putting the pathogens into a surface water receiving body that it's a problem. If the discharge goes into the soil, then I think you're okay.
Yes, we are doing infiltration now. We are putting in the soil all the effluents. But the regulation here in Ecuador does not consider the possibility to infiltrate it to the soil. So if the ministry want to go here and measure, they will measure the effluent from the last tank or from the wetland, and they will find pathogens. So this is a legal problem. We are talking with the ministry and with the regulations here, but that is the only point.
Thank you. Do we have any other question? I see that we have one in the chat. This says, can you use the gas from the biodigester to heat it more, or does it fail?
Yes, look, usually I was working before more with farmers and using manure. So we were producing a lot of biogas, enough for cooking, enough to run machines. But now with these systems, you produce just very few amount of biogas. In my family, we are producing 67 liters per day. Just to take how much is this is more or less to be cooking for 20 minutes in a stove. So it's not too much. Who wants to cook every day 20 minutes in a stove? You can storage this gas and to cook 2 hours per week. Okay, you can make the coffee during the Saturday, for example, with this gas. But if you want to use this gas to heat the digester, you begin to complicate the system, because you will need to heat a water or a fluid, and later this fluid has to go inside the digester. You will need a pump or something to recirculate it. You need to insulate the digester in these conditions, because if you heat it, you need to keep it warm. So you began to complicate it a lot. We never heat the digester using the biogas. The idea is, if you want to heat the digester, you can use solar radiation. That is what we did before in Bolivia.
I hope that answers the question. We have another one.
Yeah, thanks. Really enjoyed your talk, and it's opened my eyes to a problem I've never thought about. So thank you for that. Question was that quite often in more temperate climates, we are using organic waste not for producing biogas, but actually more as a fertilizer in agriculture. And I wondered whether that would be an option for some of the areas you've been working in, or whether that is logistically very difficult or economically not possible as an alternative to the biogas digestion.
So you are proposing not to produce biogas, to produce fertilizer.
To use it as organic fertilizer in agriculture,
Yeah.
yes.
When you use this kind of digesters, you are also producing a fertilizer. The effluent from the digester in normal conditions, not this kind of wastewater treatment, more when you are working in farms with cow manure, pig manure, the effluent is also a fertilizer, so the people can use it in the crops. But I agree with you. No, it's not all the time digesters. You can use also composting or other kind of solutions that for me are very, very okay. That depends on the conditions. For example, here in the jungle, you have a lot of humidity, so it's all the time raining. So dry toilets or composting is not too easy, because it's raining all the time. So you need to cover the place where you are doing in compost. Make some difficulties, and people don't want to, for example, in this case, they don't want to be in contact with this waste, and it's normal. Nobody wants to be in contact with this kind of waste because it came from the toilet. So it's very different when you work with toilets and when you work with farms. When you work with farms, for me, it's easier, because the people who work in the farm, they don't mind to have the manure around, to smell the manure. It's manure from the cow, so it doesn't matter. And they don't mind the fertilizer that came from the manure from the cow. It's okay for them. So it's very different when you work with toilets or farms. And for me, it's okay if you have an alternative to use it as a fertilizer. It's okay, but usually in wastewater we don't use it, because pathogens. We are afraid of pathogens, so we avoid it. So that is why we infiltrate all the wastewater inside the soil. But look, some of the nutrients, they are being recovered in the wetland. So some of the nutrients that go outside of the effluent and go inside the wetland, in the wetland, the plants are growing, taking and recovering these nutrients. So later you just take your big knife in the jungle, just cut the plants in the wetland, and you put it on the crops. So you are putting these nutrients on your crops. So you are not losing the nutrients. I don't know if I answer. Sorry.
Okay, we have a couple of minutes. No.
Yeah, I'm just interested in the very high mountain wastewater treatment system that you explained, Jaime. The wetland there, is that really a wetland, or was it just a trickling filter? Because I didn't see any vegetation there, so can you call it a wetland?
Look, yes, no, and I am agree with you. Also, this wetland, we had problems because the pipe that goes from these digesters to the wetland got frozen, and water was not going to a wetland. Also, there were a storm, and we lose the cover of the wetland. But now, I have been just 1 month ago, we were seeing what to do with this wetland, and now we find some plants here. So we were talking that we can use this kind of plants that are growing at this altitude. to try to put some artificial wetland there. At the moment, it's just infiltration. It's going just outside. But we want to improve it to convert it as a wetland with plants. Because now we are finding plants at 5,000. Before there weren't, but this is climate change.
Yeah, but I mean, you might find that I don't know if you've got any data, but you may find that even putting the effluent through that aerobic trickling filter effectively, that you will get a water quality improvement in that aerobic step. Although it's not strictly speaking a wetland because it doesn't yet have plants, but it still may have some benefit to improving water quality coming out at the end.
Yes. That is the idea.
Well, sadly, we don't have more time for questions, but I understand that if any would arise, they can contact you. So with that, I think that we can concluded the seminar. Thanks for the audience, and thanks, Professor Jaime. So one last round of applause. It's okay with you.